Hello.
Hello, Prof.
Hi, Gloria. How are you?
I'm fine, Prof. How's
I
your
got
day?
your email. I thought I'd help you out while we're waiting for everybody to get here.
Okay.
So, are you using a calculator when you do these things?
Actually, I was been using my phone.
Okay.
Yes.
And are you using the calculator on your phone or
Yes, the calculator on my phone.
okay? So, probably the best thing to do is uh, go to Google. Google has a nice calculator. So, if
Okay.
you just type to calculator, it'll take you right there. And so you'll get this thing here. Okay.
Okay. Yes,
And
Prof.
if you wanted to take a normal square root of something, like say we wanted to take the square root of 25, we would just hit this root button. Oh, sorry. I'm sorry. Hold on a second. Just hit the root button, and then 25, and then that'll give us our answer, right? But for
Okay.
calculating using the Stefan Boltzmann relationship, when you're back calculating to try and get the temperature, you need to take the fourth root of something, right? And so for that, what you want to do is uh, you put in your number. So, like, say uh, when you do your
238.
relate, huh?
I was trying to give a value 238,
Okay, that
a
would be
number.
238 is probably small of a number
Okay.
at this stage, right? Well, let me just get a bigger number. So let's just start with this number here. If you want to take the fourth root of it, you'd go to inverse, and then you pick this little thing over here, where you see how it's got the root symbol, but now there's this little box there, right? And so we'd put
Okay.
in 4 for the fourth root of that, and then hit the equal sign, and it'll give us a number. Okay.
Yes, sir.
So I'll go through that again one more time. You have in the number you want to take a root of, like say I'm going to have this large number here. You go to the inverse, you select this y root of x thing, and you get that
Yes.
little box here now. And then you can put in the 4 for the fourth root of this number, and then hit your equals, and it'll give you that.
Okay.
Okay. So the question then becomes, how do you get, the number that goes in, um, into the little box, right? Before you do that. So let's see. It's over here. So um, when you're using this formula and you're doing the fourth root, like you were giving me a number that was like 300, right? That's the number for the top here. Don't forget to divide by the Stefan Boltzmann constant, right? And the Stefan Boltzmann constant is 5.67 times 10 to the negative 8. So 567 times 10 to the negative 8. And so when you divide something by 10 to the negative 8, it's going to be like multiplying it by 10 to the 8th, right? So it's going to be a lot more. So it'll be a very large number. So this 238 will end up being pretty large. So one way I could do that is let me click here. So if I had 238, and then I'm going to divide that by 5.67 equals that. But now I'm going to multiply it by 10 to the 8th. Because dividing by 10 to the minus 8 is the same thing as multiplying by 10 to the 8th. And so now I get this really big number, right? And now to take the fourth root of that, I just go to inverse my y root x, and then I want to take the fourth root, and I get 254 in that
All
case.
right.
Or as we had said, 255. For the stuff you're doing so far, you can round. When we do a little bit more, the rounding is going to be not as allowable, and you'll see why. But we'll get to that after this.
Okay.
So has everybody, I'm going to check right now. Let's see who's all done their flips. So I want to hear about Planet Krypton. And I only have one person who's done their, Caldrian has done his basic climate model.
Climate?
It's the only one I've got on there. So Naimungo, I need one from you.
Climate change is everything.
Desire from you, all of you. I need you to do that because I want to see how you work through it, right? Now that's a 2-layer atmosphere. And so you'll want to rewatch that video. You'll probably need to watch it a couple times as you're doing it, right? And kind of take each step at a time, check your calculations, and then and see that it's following along with how we do it, and see what you get. Any questions on that?
It's okay.
Here's the stuff for the 1-layer atmosphere, but you're going to be doing it, a little. Just remember that the first flux is the energy coming in, and then the next flux is the energy going out of the planet, because we're assuming we're trying to calculate the temperature at equilibrium. Where is the temperature going to settle at? Given these constraints of how much can go out, we need the energy out to equal the energy in. That's our equilibrium constraint. Just like if I have, something sitting here at, it won't let me, if I have something here at room temperature, it's been sitting around long enough that the energy in is equaling the energy out. And so its temperature is going to end up being the same as the temperature around it. Okay. As the energy coming in, it's going to equal to the energy going out. And that's its equilibrium state. Has anybody tried doing the climate modeling and they're having problems with it? I'm curious why no one's put up their flip yet on it.
Hello, Prof. Yeah, I had a challenge, but I got it when you explained earlier on. That on calculating the temperature now. But now
Say that again. You broke up a little bit.
I'm saying I had a challenge when I reached to calculating temperature on 4th, but now I've got it. I'm going to upload.
Okay. Okay. And remember, when you do these flips, there is an option in Flip to upload like a picture to the screen while you're talking. And so, one way to do something, if you're writing it out, you can take a picture on your phone and then upload that picture into your video while you're talking, display it. If you've got access to slides, like PowerPoint, then you can take the PowerPoint slides that, are up on Moodle, and you can do your own PowerPoint slides. And I've been sending them out, but if you need a PowerPoint slide, let me know, and you can adjust the numbers and do that stuff there. However you want to do it is fine. Drawing it is fine, taking a picture, but it's going to be a lot easier to explain if you have that diagram. So I know what numbers you're getting out, what numbers you're getting in. It'll allow me to figure out if you're making a mistake or if everything's, going well.
Hello, everyone.
If that makes sense. So like, for example, here's Caldrian's video, and you can see he's drawing in some fluxes, etc. I don't want to go through, but now you're calculating for this fictitious planet, so it's going to have a different solar constant, it's going to have a different albedo, and so you need to plug those in your equation because your energy in is going to be different than Earth. For Earth, because of our albedo at 0.3 and our solar constant of 1360, our energy in ends up being 238 watts per meter square. Okay, it's going to be different on planet Krypton because it's, you know, where Superman's from. It's different. So today's lectures actually kind of build on that stuff. So okay, Shepard, you're nearly all the way done. You just got a couple things to figure out. Abood, how about you? Where are you at on your flip on Krypton?
I'm working on it.
Okay. Are you
Probably
struggling
I'll be
with
able
it?
to submit it tomorrow.
Okay. Are you
Not
struggling
that
with
much
it, or
only, but I'm just looking. No, I'm just okay. I'm okay. I'll
Okay.
complete it by
okay?
tomorrow. Yeah.
Desire, have you been working on it?
Yes, I'm working on it, but
Okay.
I'm
Are you
lagging behind.
struggling with it, or is it making sense to you?
It is, but I haven't gotten a good grasp of it.
Okay. Okay. So keep working at it. Now, is there any questions you have about like what it means, or is anything confusing to you about these calculations?
Not really. I did go through the past recordings, and I am doing as much examples that I can so that I can like grasp it proper. I just need practice.
Mm-hmm. And it takes some practice to do. It really does. You got to get used to the order in which you figure out your forces. But remember, this is predicated on the idea that energy in equals energy out. And so that's the end stage of figuring out what the temperature, what's going on the planet, what the climate is on the planet, because that's the equilibrium point. And I got really confused when I first started learning this, to be honest, because I'm like, I always try and picture things in my head, and I imagine the sun coming down and shining. Okay, we're getting energy, and now the earth is heating up. But I was having a hard time because I'm like, well, it takes some time for the earth to heat up. You know, how is this instantly sending all, you know, the atmosphere instantly sending all this to space? That's because we're looking at once it's reached equilibrium. You know, just like the objects in our room, if you take a turkey out of the freezer and you put it at room temperature, when you come back in a day or two, it will have reached equilibrium and it'll be the same temperature as the room. But in the first half hour, that turkey's still frozen, right? And so there's a difference between what happens immediately and what happens once it finally reaches its equilibrium. And in all honesty, that's kind of where we're at in our world. We're not actually living in equilibrium at the moment. So this is actually the topic of today's, which is why I timed it for when you guys are turning these things in. Caldrian, you're not here, but hopefully when you watch this, I liked your video. We'll go over it in a little bit. So we're going to talk about the transient warming. So I don't want to confuse anybody because you're still working on your equilibrium calculations. But I do want to kind of talk about before you reach equilibrium. And I don't think I understood the equilibrium stuff until I saw and learned a little bit about this. Okay, so this lecture is going to be on transient warming. So this is what happens like right after you take the turkey out of the freezer. Okay, for all the calculations you're doing in your flip grid, you know, for planet Krypton, we're explicitly assuming that it's reached equilibrium. In other words, energy into the planet is going to have to equal energy out of the planet. And so you're figuring out what the effect is if the planet has an atmosphere, what that effect is, how much it's going to change the surface temperature in order for the part that's radiated out to space to be equal to what's coming into the planet. And we derive, you know, all of the stuff you're going to be doing in that flip is all coming from this equilibrium assumption, okay? But we don't really live in an equilibrium world, right? We're doing things to the planet now. In the last videos, you know, when we talked about the carbon cycles, you know, we looked at how CO2 cycles throughout the planet into the atmosphere and into the oceans and into the land biosphere and even into the rocks. And for a very long time, there was a balance of CO2, but we saw last time in our last discussion how humans have created a new pathway from taking carbon out of the rocks and putting it into the atmosphere much quicker than it would ever happen naturally. Normally, through the process of volcanization, volcanism, that takes millions of years to really have effects. Same thing with pulling carbon out of the atmosphere in the form of chemical weathering in rocks and transferring CO2 into rocks. And so we're throwing a lot of carbon in the atmosphere. We haven't reached our equilibrium yet. Okay. And to kind of do this, to talk about it, we're going to do some more of these little pictures. So let's just start with an Earth with no atmosphere. Okay. We've already calculated the flux into the Earth at about 238 watts per meter squared. And that was based on our solar constant and the albedo for the Earth, right? I'm going to go way down here. So that was based on these calculations here. Our solar constant and our albedo, we plug those in. We know energy coming in from the sun based on our location in space, how far we are away from the sun and how hot our sun is, how much energy it generates. That gives us our solar constant. Our albedo is how much gets reflected back into space. So 1 minus the albedo is the fraction that actually hits our planet. And when you calculate that energy in, divided by 4, that's 238. So that's where we get that number 238 coming from. Okay. And if we assume our equilibrium condition that the energy in equals energy out, that would put the planet at 255K, right? Because if the energy out of the planet is 238, then what we have to do is figure out, well, if the energy is 238, then what's the temperature, right? And so we get to use our fun formula that allows us to calculate the temperature, right? That's our fourth root. You know, it's the fourth inverse of the of the Stefan Boltzmann relationship. Okay, so that's where we get our 238 from, and that's how we calculate this temperature right over here. Okay, it's our 238 divided by the Stefan Boltzmann constant, and then you take the cube root, or the fourth root of that. So that's our planet with no atmosphere. That's what we're starting with. And we're saying, you know, it's at equilibrium. Now, I want you to imagine we just instantly throw on an atmosphere on the planet. Okay. What are the fluxes right after the layer is added? Okay. So the energy into the planet doesn't change, right? It's still 238 coming down. But at that moment, at the instant right after we've added the layer, the planet's still at 255, just like it was, you know, when we were looking without an atmosphere. Okay. But right now, an instant after, the planet's at 255. Now, we know what the flux will be from it if the temperature's at 255. That was 238. So the planet is still, since it's still the same temperature, it's still emitting the same amount of energy. Now that energy is going to be absorbed by this new instantaneous layer that's just been added, right? And so now, what's this layer going to emit? 238 is coming into it. 238 is going to be coming out, but half is going to be going up and half is going to be going down. So we got 119 going up and 119 going down. Okay. Note this is different than your equilibrium constant calculations. Normally you would say, here's 238 coming in, and so I would make this 238 going out. That's assumed that it's reached equilibrium where you're at the condition where energy in has to equal energy out. But when you talk about transient warming, this is about the time in between before that happens. Okay. You can still look at energy balance though. Okay. And what do you see with energy balance? Is the amount of energy coming into the planet the same as the amount of energy leaving the planet the instant after we add the layer? How much energy is coming into the planet? How much is the sun giving us? That's 238, right? How much is going off into space?
119.
119. So we're getting more energy in than we're pumping out into space in this case, the instant after the layer is added. So the planet is no longer in energy balance. Okay. We have more energy in than we have energy out. Okay. We've got 238 coming in and only 119 coming out. And so if you take energy in and subtract energy out, that gives us a net of 119 watts per meter squared that the planet is accumulating, right? Because it's absorbing this energy and it hasn't gone out to space yet. Okay. So now what happens when an object accumulates energy? It gets warmer, right? Because remember, internal energy is what we're talking about. All this is going into the internal energy of the object. Molecules are starting to move faster as it gets this energy in there. Now we can look at the surface too. So if we look at the surface, we want to see energy in minus energy out. And so our energy in is 238, right? But it's also this other feature here that's also coming in energy to the surface now. And then the energy out, however, since the temperature hasn't changed yet, we have to subtract that because that's our energy out. And so when you add all those up, you're going to find there's that same 119 watts per meter square. In other words, the planet was accumulating energy, and it's really all being accumulated at the surface, right? Because the surface is going to be what emits this energy coming out of it. But right now it's still 255 because this is just an instant right after we've added our atmosphere. And things have temperature has a certain amount of inertial energy, right? Certain amount of inertia. That's why it takes a while to boil a pot of water if you're cooking it on the stove. It doesn't happen instantly. It takes a little while to get those molecules moving. So if we're accumulating energy at 119, we would expect, since we're accumulating energy, the temperature is going to rise. Okay. Now let's just say, I'm just going to pick a number. Let's say it goes from 255. We know it's accumulating energy. Let's say it rises to 270 Kelvin. Okay. So now what's our energy balance? At 270, if you use Stefan Boltzmann, that's going to radiate at about 300 watts per meter square. That's what's now coming out of the planet. Okay. That's going to be equally divided. And so that's 150 up and 150 down. And so our energy's still not balanced. We're still taking more energy in than we are getting out, to a tune of 88. So how did I get this plus 88? Where's that coming from? When I'm looking at, for the planet, energy in minus energy out, what numbers am I using to get this plus 88?
The 300 minus 238.
300
Like
minus,
300 minus 38.
what's the energy coming in from our planet into this planet?
238.
And what's the energy leaving? Well, you're going off into space now. We're looking at that. So 150. So 238 minus 150 is giving you plus 88. That's for surface. Now, if you wanted to look at the surface, you could say, well, the surface has 238 coming in and 150 coming in, and then subtract 300. That's what's going out. It'll give you the same number. 238 plus 150 minus 300 is going to be that 88 as well. So you can do it either way. You can either look at the surface or you can look at the whole planet, but you'll still find that we're accumulating energy. Just like we were before. Remember before, it was looking like this, 238 coming down, the temperature was only 255. So it was emitting less. It was emitting 238 because it was in energy balance before. Now we've instantly added this atmosphere, which is going to re-radiate down and get us to this point. Okay, so it warms the planet up. Now notice that our energy balance, the difference is less than it used to be. Okay, if I go back, we were accumulating energy at 119 watts per meter squared before, when the planet was only 255. But now that it's 88, now that it's the temperature's increased from 255 to 270, we're no longer accumulating energy at a rate of 119. We're now only accumulating energy at 88. Okay, so what does that mean? We're getting more energy in than we are energy out. So what's going to happen to the temperature?
You're hot.
It's going to increase.
Right, your temperature is going to increase. Whenever you're getting more energy in, then you are getting rid of energy. You're accumulating energy that makes your temperature rise. So in this transient example, we've suddenly added a layer. The planet was the temperature it used to be. Now it's warming up. It's gotten up to 270. It's still warming, right? Because it's still accumulating energy. And so we got to go up in temperature. And so now let's go to 295. What should our fluxes be here? Well, you take 295. You can use the Stefan-Boltzmann to determine how much energy that's going to radiate. And what you're going to end up finding is you're at, is that right? Yeah, 429. If 429 is going out, getting absorbed by the atmosphere, then half is going to go out to space and half is going to come back down. So now our fluxes are 238 minus 214 for what's happening to the planet. And so our energy imbalance now is only plus 24. Before it was plus 88, and before that it was plus 119. So you can see that as it's heating up, the flux, the difference is starting to decrease. I can imagine you can see where this is going, right? But when will the temperature stop increasing?
You come again, Prof. Seems I lost you.
So you can kind of see where this is heading. When we first started and the planet was only at 255, we were accumulating energy at 119 watts per meter squared. And that was causing the planet to warm. And we went up in temperature, I think 275, and then it was only accumulating at 88 watts per meter square. Now we've moved further up in temperature, but now the difference in energy is less, so our accumulation of energy is less. Now we're at only plus 24, okay? At what point, so it seems like as the planet gets warmer, it slows down how fast it's warming. At what point is it going to stop warming? When will it get to, it doesn't, like if these numbers are getting lower and lower, when will it stop accumulating energy? Shepard, do you care to take a stab at that question? Okay, well then this is a good exercise because you guys, so let's run just a little bit. Okay, so we started with a planet that was at 255. 238 was coming in. Now, because it's at 255 right now, it's emitting at 238. Okay, now we suddenly add an atmosphere. And so we're still emitting at 238. And since we're emitting at 238, some of it's getting trapped by the atmosphere and only some is going up and only half is going up and the rest is coming back down, right? And so half of this was only 119. And so the planet was taking in 238, but only letting out 119. That gave us an energy imbalance, right? 238 was coming in, only 119 was leaving the planet. So that means Energy in minus energy out, that means we were accumulating energy at 119. Because at 255, we're only emitting 238, which means half of that's getting out of our atmosphere. Okay. Since we're accumulating energy, our temperature is going up. So if the temperature goes up, let's go to a higher temperature. So I just picked a higher temperature of 270. At 270, you can calculate that the radiative energy, the black body radiation, would be around 300. Again, half's going to go into space and half's going to come. So this layer of atmosphere is going to stop half of it. And so only half will go out in space. And that means now, if you look at energy in versus energy out, it's 238 coming in minus the 158 coming out. That's now we're accumulating energy at 188. That's because the temperature is 270. Remember before, we were at 255. It was accumulating at 119. So the amount that we're accumulating when we're this temperature is a lot. It's the most. Okay. And then when we go to a higher temperature, we're now accumulating energy at a slightly less number, because this more is getting radiated out into space because the planet is radiating more. Okay. And since there's still more energy coming in than there is energy going out, 238 coming in, 150 going out, we're accumulating at 188. That means the planet will still continue to warm. So it heats up. So we'll go to 295 now. We could have picked 285. We could have picked 280. We could have picked 290. We're just saying it's getting warmer. At some point, it's going to get up to this temperature. And when you calculate the amount of power being radiated from our black body, which is the planet, 295 gives us 429 watts per meter. Well, half of it gets reflected back because of the atmosphere, and the other half goes out. So now what's leaving the planet is 214, but we're still taking in 238. Now the difference here is smaller. This is less than the 88 before. And so it seems like as we rise in temperature, the difference between energy in and energy out is getting less and less and less. At what point, and this is my question, at what point is it going to reach, its final temperature? At what temperature will it stop rising, or how do you figure out that temperature where it stops? Because right now we're accumulating energy much less than we were before. And if we go up a little bit in temperature, it will be accumulating a little bit less. And if we go a little bit higher in temperature, it will accumulate at a slightly slower rate. Eventually, you're going to get to a temperature at which it stops accumulating energy. What point is that?
Hello, Prof. Is it not when you balance energy in and energy going out?
Exactly. And that's what I need your brains to come to that point, is when you reach energy balance, when you finally get to energy in equals energy out, then the warming stops. That's our equilibrium state. Okay. All the calculations you're doing when you're doing that flip grid on the planet Krypton, you're all assuming that it's had enough time to reach its equilibrium state. So the energy in equals the energy out. And so you can calculate the final temperature that it settles at. because the temperature won't continue to rise because you won't be accumulating energy anymore. And so that's why we do the energy in equals energy out. That's our equilibrium state. That's the state at which it stops changing temperature. When it's equal to its surroundings. It's not taking in more than its surroundings. It's not releasing more to its surroundings. It's in equilibrium with its surroundings. And that's when the temperature stops rising. But notice it took some time, right? And that's the state we're in right now because we've thrown carbon dioxide into the atmosphere. We haven't reached equilibrium yet. We're still in the process of getting to that equilibrium state. And that's what we'll be talking about in the next few lectures is that process of getting to the equilibrium state. Because then it really, you'll see where all this comes together, why we're talking about this, because we're going to be able to pin some actual numbers with amounts of CO2 and see what we expect in the next couple of years. You know, we could calculate based on some final CO2 concentration, maybe, you know, layers of atmosphere, what our final temperature is going to be at. But how long does it take to get there? 1 million years? 10 years? How fast are we going to be warming? And that's a really critical thing to understand with climate change is what that rate's going to be. And when you add a little bit of CO2, how long does it take to get out of the atmosphere? And until then, how long does it take for the Earth to warm up? So I really hope this didn't confuse you in terms of how to do the Krypton. Because remember, in planet Krypton, or assuming energy balance, energy in equals energy out. The amount coming into the planet is always going to equal the amount going out into space. And then you back calculate everything until you figure out how much energy the planet has to be radiating into the atmospheres. And once you know how much the planet has to be radiating, then you can tell what temperature the planet is. And that gives you the equilibrium state when the planet finally reaches its equilibrium temperature and you stop heating up. Gloria, you look unconvinced.
Prof, I'm just wondering when that will come to pass.
Okay. Well, it's kind of scary and it's kind of complicated. We'll get through some of that and we'll find out what variables it depends on, because there are some variables that are good, some variables that are bad, and we're going to see that it's not just the amount of CO2 that we add in the atmosphere, but when you warm the planet has effects. And so you have these feedback loops. Like, for example, if the planet warms, the ice melts. If the ice melts, your albedo changes. Unfortunately, it gets to be less, so you reflect less out, so you accumulate more energy. And so that makes it warm faster or warm more. And so there are lots of different feedback loops that we'll discuss that will all fit into here, and you'll see why we did these numbers in the first place. We just got to walk along just a little bit further. But everybody, please try and do your equilibrium calculations on Flip. And then once you get them up there, it's okay if you get stuff wrong, okay? And not everything has to be right. It's okay to get it wrong. It's the process of doing it. And then when I see how you do it, if you document how you're doing it, I'm drawing this line now and I got this number, and now I'm doing this line and I got this number. If I see how you're doing it, when I videotape my response, watching it, I can say, oh no, you needed to do this number. I'll be able to give you a lot better feedback if I see you working on it, which is why I want you to do it. I care less about if you get the right number than for you to tell me how you're doing it and how you think it works. And then I can give you some, you know, some better advice, so it works out better. So please get those done this today, if not tomorrow, so I can give you guys some responses, because I hate to throw out new calculations before you're done with the old ones. And if you're having problems with the calculator stuff, you know, use the Google calculator. There's also plenty of YouTube videos on how to use the calculator. So before this class, I just did a little search on an easy way to get fourth roots on the web. And I said, oh, use Google Calculator. And there was this little video I watched like literally 2 minutes before class where I'm like, oh, do that. Okay. So, well, so long as we work together, I think we'll get through this. On a different note, in a couple of weeks, we're going to have a guest speaker. Dr. Farusa from Africa University is going to do a presentation on talking about climate change. And then in a few weeks after that, in November, one of my former students, who's actually a senior scientist at Novartis Pharmaceuticals, he's from Zimbabwe. And he's going to come and talk to you all, not necessarily about global warming, but he's been very successful coming from there to here and going to school and all that kind of stuff. And he's been helpful in getting a lot of people from various countries into some neat, successful routes and stuff like that. And so you'll have some fun talking to him, I'm hoping. But thanks, everybody. Have a great weekend.
Thank you, Prof.
Thank you, Prof.
Grateful.
Okay. We all going good? Any advice on how I should be doing some of this differently?
Everything
You're
is
doing
okay.
Okay. If you got any tips, I'm always happy to take criticism. Just shoot it in an email and I'll try to, you know, keep that in mind the next time I go on one of these long spiels. Thanks a lot. Have a great day.
Thank you.
Bye.